Good morning, dear student. I am Dr. Indira, Department of Physics, Doon University. I will teach you the subject Quantum Mechanics in semester 5. This course has 6 credit, 4 credit for your theory class and 2 credit for your lab examination. If we talk about marks distribution, this paper is of 100 marks, and among that there is mid semester examination of 30 marks and end semester examination of 30 marks with 20 marks for assignment and 20 marks for your lab examination. In assignment, there will be 10 marks for your board presentation or PowerPoint presentation and 10 marks for your class notebook. And in laboratory exam, I will teach you to make Scilab program for the topic of quantum mechanics. So in this video lecture, I will teach you the topic potential well. So this is the content of this video lecture. Wave function and its physical interpretation, Schrödinger equation for a quantum particle, boundary condition, solution of Schrödinger equation in 1D infinite potential well, energy eigenvalues and wave function for potential well. So after this video lecture, you will be able to learn quantum particle can be represented by a wave function, physical interpretation of wave function, time independent Schrödinger equation, application of boundary condition, quantum particle has discrete energy value. So, in quantum mechanics, we describe system using wave function. When we treat a system as a wave, the wave function represents the displacement of the wave. If we treat the system as a particle, then the wave function is used to give us the probability of finding the particle of some same point. In order to describe any system in quantum mechanics, we must be able to determine what the wave function is numerically. The Schrödinger equation is a differential equation that we can use to solve for the wave function quantitatively. In the same way that Isaac Newton invented the second law of motion F equal to ma, the Schrödinger equation was invented and confirmed using experiments. This means that there is no way to derive this equation. In order to determine what form the equation takes, we will use the conservation of energy. We will also assume that the wave function does not depend on time and only depend on the position of the system. Suppose that a particle is moving in x direction, no force is actually acting on the particle. For example, we have an electron moving along x positive direction. By Louis de Broglie principle, lambda equal to h upon p, where h is Planck constant and p is the momentum. In step 1, wave produced by a particle such as electron moving along x-axis, we might expect that wave function satisfies a differential equation psi x t equal to a sin kx minus omega t plus b cos kx minus omega t. Since t equal to 0, as this is time independent Schrödinger equation, psi x equal to a sin kx plus b cos kx. It gives the equation of wave function where k equal to 2 pi by lambda or 2 pi p upon h or p upon h upon 2 pi, which is nothing but h cross. So k equal to p upon h cross. In step 2, we apply the law of conservation of energy. H equal to E equal to kinetic energy plus potential energy. After putting the value of kinetic energy, we get E equal to k square h cross square upon 2m plus v. Let us take second derivation of equation 1. We got d2 psi upon dx2 equal to minus k square a sin kx plus b cos kx, or d2 psi upon dx2 equal to minus k square psi x. Now multiply equation 3 by minus h cross upon 2m. We got minus h cross upon 2m d2 psi upon dx2 equal to k square h cross square upon 2m psi x. If we take equation second and multiply both side by psi x, we get e psi equal to k square h cross square upon 2m psi x plus v psi x. E psi x equal to v psi x minus h cross square upon 2m d2 psi x upon dx2. This is the time independent Schrodinger equation. Now, I will discuss the physical interpretation of wave function psi. A satisfactory interpretation of the wave function psi associated with the moving particle was given by Born in 1926. He postulated that the square of the magnitude of the wave function mod psi square or psi star, if psi is a complex function evaluated at a particular point, represents the probability of finding the particle at that point. Mod psi square is called the probability density and psi is the probability amplitude. According to this interpretation, the probability of finding the particle within an element of volume d tau is mod psi square d tau. Since the particle is certainly somewhere, the integral of mod psi square d tau over the whole space must be unity, that is, integration minus infinite to plus infinite mod psi x square dx equal to 1. A wave function that obeys this equation is said to be normalized. Every acceptable wave function must be normalizable. Besides being normalizable, an acceptable wave function psi must fulfill the following requirements. Number 1. It must be finite everywhere. It must be finite everywhere. If, for instance, psi x is not finite at a particular point, it would mean an infinitely large probability of finding the particle at that point. This would violate the uncertainty principle. Therefore, psi must have zero or finite value at a particular point. Number 2, it must be single value. If psi has more than one value at any point, it would mean more than one value of probability of finding the particle at a point, which is obviously ridiculous. Number 3, it must be continuous and have a continuous first derivative everywhere. This is necessary from the Schrodinger equation itself, which shows that d2 psi upon dx2 must be finite everywhere. This can be so only if d psi over dx has no discontinuity at any boundary where potential changes. Furthermore, the existence of d psi over dx as a continuous function implies that psi 2 is continuous across a boundary. These requirements, which must be fulfilled by an acceptable wave function, carry great significance when the Schrodinger steady state equation for a given system is solved to obtain a wave function which fulfills these requirements. Then we find that the equation can be solved only for values of the energy of the system. Thus, energy quantization appears in wave mechanics as a natural feature of the solution of the wave function. The values of energy for which Schrodinger equation can be solved are called eigenvalues and the corresponding wave function are called eigenfunction. Eigenvalues and eigenfunctions. If psi is a well-behaved function, then an operator P may operate on psi in two different ways, depending on the nature of the function psi. Number 1. The operator P operating on the function psi may change the function into another function phi, that is P psi equal to phi. Then the new function phi will in general be linearly independent of initial function psi. Number 2. The operator P operating on some function psi may leave the function unchanged but with a complex or real multiple, that is P psi equal to lambda psi, where lambda may real or complex number. In this case, the function psi is a member of the class of physically meaningful function called the eigenfunction of the operator P associated with eigenfunction psi. Equation 2 is called an eigenvalue equation. Boundary condition. Boundary conditions are conditions which should be satisfied by the wave function and its derivative at the boundary of a potential value. It helps to find the solution of Schrodinger equation and also determine the possible values of energy and wave function, etc. Conditions. Wave function must be continuous and derivative of wave function must be continuous. 1D potential well. Let us consider a particle in a box in which a particle of mass m is in between two walls x equal to 0 and x equal to a. The wall of the box are rigid perfect elastic and non-penetrable, so that the probability of finding a particle outside the box is zero. Potential energy inside the box is zero and outside the box is infinite. Time independent Schrodinger equation is minus h cross square upon 2m del square plus Vr psi r equal to E psi r. The general solution of this equation is psi x equal to a sin kx plus b cos kx, where k equal to under root 2 me upon h cross square, where a and b are arbitrary constant. Now let us apply boundary condition. At x equal to 0, psi must be 0. So this boundary condition gives us psi 0 equal to a sin k0 plus b cos k0, and this gives b equal to 0. The another boundary condition is at x equal to a, psi equal to 0. So this gives psi 0 equal to a sin ka plus b. So a sin ka equal to 0, but a can't be 0 as b already gives us the value 0. So sin ka must be 0, and we know that for all n pi values sin must be 0. So this gives us the value of k equal to n pi upon a. Now after putting the value of k, we can evaluate the value of energy. So we know that k equal to under root 2 me upon h cross. So this gives E equal to n square pi square h cross square upon 2 ma square. So now let us calculate the energy eigenvalues. For n equal to 0, E1 equal to pi square h cross square upon 2m square. For n equal to 2, E2 equal to 4 pi square h cross square upon 2m square, that is 4E1. For n equal to 3, E3 equal to 9 pi square h cross square upon 2ma square, that is 9E1. For a particle confined inside a given potential well, the solution of Schrodinger equation will consist of discrete quantized set of energy. Let us now consider the eigenfunctions of the particle. Substituting b equal to 0 and k equal to n pi upon l in equation 1, we find that the allowed solution of Schrodinger equation is psi x equal to a sin n pi x upon l. To find the value of a, we use the normalization condition, that is integration minus infinite to plus infinite mod psi x square dx equal to 1. So after solving this, we get the value of a equal to under root 2 upon L. The normalized eigenfunction of the particle is therefore psi x equal to under root 2 upon L sin n pi x upon L. The first three eigenfunctions psi 1, psi 2 and psi 3 together with the probability density mod psi 1 square, mod psi 2 square and mod psi 3 square are shown in figure A and figure B. It is obvious that the wave mechanical result is very different from the classical result. Classical particle being anywhere in the box, wave mechanics on the other hand predicts that the probability is different at different points and there are points where the particle is never found. Further, at a particular point, the probability of finding the particle is different for different energy states. For example, a particle in the lowest energy state is most likely to be in the middle of the potential well, where middle of the potential well. Minimum energy of the particle in 1D potential well cannot be zero. It is obvious that quantum number n cannot be zero, because this would make psi x equal to 0 everywhere in the box, which means that the particle is not present at all. Now the exclusion of n equal to 0 means that the particle cannot have zero energy. This quantum mechanical result has no counterpart in the classical mechanics, where all energy including zero are possible. The lowest value of n is 1, and thus the lowest allowed value of the energy is even equal to h square upon 8 ml square. This is consistent with the uncertainty principle. Since the particle is confined to the box, the uncertainty in its position is equal to the length of the box, that is delta x equal to L. The uncertainty in its momentum must therefore be by relation delta x into delta p is greater than or equal to h upon 4 pi, or delta p is greater than or equal to h upon 4 pi L. And the uncertainty in the energy would be delta E equal to delta P square upon 2m is greater than or equal to h square upon 32 pi square ml square. So this minimum energy must be of the same order as the uncertainty in energy. This is consistent with the value obtained by putting n equal to 1 in the energy expression. Thus, the uncertainty principle provides confirmation that E equal to 0 is not admissible. Why are we not aware of quantization in daily experience? In our daily life, we come across particles of large mass and systems of large dimensions. In such case, the allowed energy state do not appear to be quantized and for all practical purposes from a continuum. To show that, let us find the spacing between two adjacent energy level for different values of the mass of a particle moving in a boxes of different sizes. The difference in energy of two adjacent level is delta En equal to En plus 1 minus En. After putting the value of En plus 1 and En, we got delta En equal to h square upon 8 ml square into 2n plus 1. Let us take m to be the mass of a molecule equal to 10 to the power minus 26 kilogram and L to be 10 centimeter. That is, for the molecule of a gas in a vessel, we have delta En equal to 3.4 into 10 to the power minus 21 2n plus 1 electron volt. The permissible energy levels are so very close together that they may be regarded as being practically continuous. Although energy quantization occurs in principle, it will not affect the motion of the molecules. Hence, in the domain of everyday experience, quantum effects are imperceptible. This accounts for the success of Newtonian mechanics in everyday life. A similar result is obtained if we take m to be the mass of an electron but L same as above. In the case of free electron in a metal, we have delta En equal to 3.8 into 10 to the minus 17 2n plus 1 electron volt. Thus, in a trap of a macroscopic size, the energy of an electron behaves in classical manner. It can take continuous values. An absolutely different result is, however, obtained for an electron moving in a region of atomic dimension. In this case, delta En equal to 38 2n plus 1 electron volt. The spacing between the lowest and the next level is 114 electron volt and increases in higher adjacent levels. Thus, these energy levels are sufficiently far apart to make the quantization of energy conspicuous. Thus, in passing from atomic to much higher dimensions, the result of wave mechanics approach those of the classical physics. These are reference books